Coming with a new sound. Who the said that we just underground? Sprint up pound, right in that lab. Blowing the glass of the ceiling, I'm faded, I'm out. They hating but seeing me now. My third eye blind for the night. Can't see me, no how. My flow's me, oh pal. Man, them putting the replay. You can't tell. Looking like new car smell. Bad to the bone, little homie skinny bound. Take two, pass round. We don't pass out. Only come out when the sun goes down.
Don't nobody know my name. My music I be played. Always faded, talking. I'm doing my own thing. Ain't nobody tell me nothing. I'm hard-headed and stubborn. My mates all in the club yelling. You claiming my name. See, I do what I want. You do. I do what I want. You do. No busters like you. No busters like you. Always talking way too much. Like you got something to prove.
Got my pants sagging, don't give a ignorant music cause I want, oh Lord, who's gonna fill up my cup? I quit drinking 2 days ago, but that little bit of drink feel amazing, no. Just one more of these and I'm out of control and no dance flow. Done told y'all I'm a trippy motherfucker by the boatload and that's black. Whoa, making that money we getting involved. Give a penny and no cover all. Doing nothing and you are not because you wanna do. Roll on my let's stop on this. Drinking my cup, I'ma fill up my globe. I will not lie, we a little bit up. We don't give a fuck, dude, that's just me. I'm doing my thing, cruising around the city like
Interesting theory, interesting idea. It's fascinating for me in the evolution of science, how somebody had the right idea and then for a long time nobody believed him. And it was only much later that we came back to that first idea. So you should draw confidence from that. It was John Dalton in the early 1800s who first started to put forward new evidence in support of the theory of atoms, and that was the foundation of modern chemistry. One of the other parts that we cover in the introduction of our Foundation 1 science course is this concept relating to phases of matter and the concentration of matter. Remember, we were speaking about here the idea that in terms of the atomic theory, the state of matter is dependent on the amount of atoms present as well as the amount of energy with which they're moving. So if I take you back down to this graphic. Oh, and a brief aside, just for the record, this live lesson, as you're probably aware, it's being recorded, warts and all, and with all the mistakes in it, okay. And this is being stored on our platform, so you're able to access a huge library of recorded materials, and anytime you want, you can go back and look at these again. So that resource is there for you. We are also collecting these lesson notes, and they will be made available to you as well. So what I'm presenting from, you're going to be able to access and use if you need to at a later stage. So don't worry too much if you see graphics and images up. You don't have to copy them down and scramble to copy everything. You're going to be able to access these at a later time when it's convenient for you. Okay, so looking at the phases of matter, this was an image I pulled from NASA resources. We see that we have solid, liquid, and gas, which by now you must be very familiar with. Let me just modify how we're looking at that exercise. Right, good page. So, a solid holds its shape. It has a fixed volume. We can say that the matter is compressed into a very small area. If you take that same amount of solid and you apply heat, you increase the energy of the particles, they move around more, the solid melts to form a liquid. The same amount of atoms now forms a liquid instead of a solid. So the shape changes. We still have a fixed volume because atoms in a liquid are attracted towards each other. They're not as free as in a gas. But what we can say is that the shape of the liquid now is the shape of the container. While a solid maintains its own shape, a liquid does not have a fixed shape. It takes the shape of whatever is containing it. I see we have a question coming up. Atom 1, I lost an electron. I'm waiting for the punchline on this joke. Okay, let's carry on with the lesson until it comes through. Are you positive? That's quite funny. I like it. Well done, Lynn. Okay, so, sorry, one more comment and then we'll continue here. Yes. Okay, so in a gas, the particles have the maximum amount of energy. If you take the liquid, you heat it, in other words, you supply energy, you overcome the forces of attraction holding those particles together. Gas particles now are free. They've got the maximum ability to move around. And like with a liquid, the volume they occupy is the volume of the container, and the shape that they occupy is the shape of the container. Just going to have a look at that comment that someone posted. What do you call an acid with attitude? It's a mean, attitude. Hilarious. Very good. Okay, so phases of matter, solid, liquid, and gas. What you guys need to remember is that we're dealing with the relationship between the particles themselves as they make up substance, and liquids having a fixed volume but a greater degree of freedom, and the shape determined by the container. The same is for the gas. Notice that a gas, the volume a gas occupies, it's the volume of the container itself. While with the liquid, the volume is determined by the amount of atoms present, making up the liquid. So there is a fixed volume. The volume is determined by the number of atoms present. The volume of a gas is not determined by the number of atoms of gas present. The volume of gas is determined by how much space there is for the gas molecules to occupy. And one last joke, let's see. I tell bad science jokes because all the good ones are gone. Excellent. That's hilarious. I love it. One last joke here, and I think that's going to conclude our session for today. What is the fastest way to determine the sex of the chromosome? Pull down its genes. That's terrible. I love it. Okay. Guys, it's been great having you on board for this live lesson. Thanks for interacting with me. And I hope that we're going to see you guys join in for more of these sessions. Every Wednesday, we're going to be continuing with them. And in between times, don't be strangers. If you need to make contact with us, and if you have any questions that you'd like to ask regarding extra information, you contact your class teacher and they will help. Okay.
Water is the most common substance around us, and in fact, we cannot live without water. We know it. But just because it is so common, perhaps we take it for granted, because water really, it's full of exceptions to the rules. And we're going to discuss one of these exceptions here. Here we have a representation, those three diagrams show a representation of how the water molecules are arranged in the solid, in ice, in solid water. This is liquid and finally gas. And an important aspect of water is that because it's made out of one oxygen and two hydrogens, we know that this type of formation of its molecule makes it a dipole. One side is more negative, the other side where the hydrogen atoms are is more positive. So here we would have one single water molecule. This part here where the hydrogens are is more positive, the other side is more negative. And what happens now is that the positive side of one molecule is attracted to the negative side of another molecule, and it has the ability to form this type of bonding, which we call the hydrogen bond. We see here, if this is one molecule of water, look at this hydrogen, it is attracted to the oxygen of another molecule. And this part here, where the two join, is due to the hydrogen bond. This is a hydrogen bond. A hydrogen bond, a very strong type of bond. And because of this hydrogen bonding, when water freezes, the water molecules are arranged in shapes like this shape here. And the result of this arrangement is that they leave a lot of empty space in between. So once water molecules come together, join together to form a solid ice block, they leave a lot of empty space in between them. Compare this empty space in the solid state of water and here in its liquid state. We see that the molecules are a lot closer together and they leave less spaces in between. And that is why a quantity of liquid water, an amount of liquid water, takes up less volume than the same quantity when it becomes solid. And here we are familiar with this effect where we place a water bottle in the freezer and the next day the water bottle might be broken because the water expands as it becomes ice and takes up more volume and the glass breaks. If it was plastic, it would just blow up, as we know from experience. Another consequence of this effect is that ice floats in water. Why does ice float in water? We know that when we have a glass of water with ice cubes inside, the ice cubes float on top. It's because if we compare a liquid quantity of water and the same quantity in its solid state, we see that here the molecules are much closer together, which means this is more dense. This is a more dense configuration of water molecules than this one. So the liquid water is denser than the solid water, and that is why the solid water, which is less dense, floats on top. Less dense objects float on top of more dense liquids. And that is why ice floats in water. Ice is less dense than water. An interesting aspect is that when we wait long enough and these ice cubes melt, the water level in the glass will stay exactly where it is. It will not go up or down. So the fact that ice takes up more space than liquid, it's an exception to the rule because normally, the norm in solids is for the particles to be slightly closer together than what they are in the liquid phase. So therefore, for all other substances, the solid has more density than the liquid phase of the same substance, but not in the water. And this is very important. In fact, all the peculiarities of water, and this is one of them only, have such an important impact in life on Earth. Which, if the water was not this peculiar substance, perhaps there would be no life on Earth. In this picture, we see how the temperature of the water changes as we go down towards the bottom up to 4 degrees Celsius, because 4 degrees is an important temperature regarding the water, because at 4 degrees it's when the liquid water is at its densest. So water of 4 degrees is very dense and goes to the bottom. Then it's 3 degrees, 2 degrees, 1 degree, and finally that's 0 degrees here at the top where the water freezes. Of course, the water freezes at 0 degrees and it will stay there at 0 degrees on the surface, because when a substance changes phase, the temperature stays constant. And in the case of water, the freezing temperature is 0 degrees, so it will stay there at 0 degrees. So below that, there will be no temperature of water, which will be below 0 degrees, and it's a protection for all the animals and plants that live below the surface, very cold climates. And that is why life continues in lakes and other bodies of water where temperatures of the air fall below, well below 0, and life continues. Another interesting aspect is that we said that ice floats in water, like the icebergs float in the sea, in the oceans, close to the Arctic and Antarctic. An interesting aspect is that if you look at this iceberg, this picture of an iceberg, here is the surface of the sea, and here is the iceberg, which is solid water, of course. Look how much is below the surface. It's only, well, if in pure water, sea is not pure water, of course, but in water, generally pure water, we would expect 9/10, the 9/10 of the volume of solid water to be under the water, and only the 1/10 to be above the water. We see that only 1/10 is above the sea level, and the remaining is below. So it's actually quite dangerous to meet and collide with an iceberg. So it's nice to know that most of the ice floating in water is actually below the surface. Only 1/10 of ice sticks out from the surface of water, which means when the ice melts, its volume will decrease by 1/10. So that remember that when ice melts, the level of the water does not drop, does not change, stays where it is. And here in the two bottles, here we have water, liquid water, and here is after we have left it in the deep freezer, and we see, although the water level was up to this mark in the bottle, after the water freezes, it expands. We can see it actually pushes the top up, and it blows sometimes if there's not enough space to expand. So we see the volume of the liquid and the solid water are not the same. What we have here is 2 glasses of water, tap water. This is the tap water. This is water with a lot of dissolved salt in it, table salt. In fact, this is a saturated solution of table salt and water, because you can see there is some spare salt at the bottom of the glass, which has not been dissolved. It means this is saturated now. Now let us compare the densities of those two mixtures. The tap water, it's also a mixture. There are some impurities in the tap water. It's not like pure water. And here we have the salty water. And how can we compare the densities qualitatively? We are going to use 2 eggs. First, let's put an egg in the tap water. Let's put it slowly. And we see it sinks. Here's the water came to the brim there. It sinks. It goes down as much as it can, as the shape of the glass allows it. Now let us put another egg, uncooked eggs. These are uncooked eggs in the second glass, the salty water, in other words, and look at this. In this glass, the egg floats. Obviously, if we assume that the eggs are exactly the same, identical, and they have the same densities, it means that the density of the egg, the density of an egg, is smaller, is less than the density of salty water. And from this glass, we can assume that the density of the egg is bigger than the density of tap water. So we see that the same object can float in a certain liquid like salty water, but it can sink in another liquid, which in this case is the tap water. We could repeat the same experiment with the eggs using oil, cooking oil, for example, instead of water, or methylated spirits or some other liquid, to compare the densities. Now let us compare qualitatively again the densities of different liquids, because liquids, being materials, are also characterized by a certain density. And we can try this provided that the liquids do not mix with one another. They are immiscible. So let us pour some tap water in this glass, say halfway. Let's fill it up halfway. We are going to compare the density of the tap water with the density of oil. But in order for us to see it better, let's put in some food coloring to distinguish it from the oil. A few drops of food coloring will do until we get a nice color. Mix it a bit. And now we are going to pour some cooking oil, ordinary oil. Now we are going to pour the oil as gently as possible, if possible, to have it hitting the walls of the glass so that it doesn't go straight in and make a big splash and breaks into droplets. So let's try and do that as gently as possible. So now that the oil has settled, we see that the oil floats on top of the water. Now this tells us that oil has density which is less than the density of water. And we can see that because oil and water do not mix. There are other liquids which have different densities, but they mix when we pour one on top of the other, and we cannot tell. But if the liquids happen to be immiscible, meaning they do not mix, then we can see which is denser than the other, because the denser one will go to the bottom and the oil will go to the top. How about if we pour more water on top of this oil? The water should go below the oil and supplement the other water. Let's try and see what happens. Let us pour some water slowly, and let's see, will it go on top of the oil or below? And we see that whatever we do, the water goes below the oil because it's denser. Of course, we could try with other liquids as well. We could pour other liquids. For example, alcohol does not dissolve with the oil, at least not very fast, so it should float at the top because alcohol has a lot less density than oil. Now let us see a little experiment which perhaps you have seen before many times, and perhaps you have tried it before many times. We are going to fill this glass with water up to the brim. And then we cover it with a piece of paper, nice flat paper, or something similar. And if we turn it now upside down, we see that the water does not spool, at least not immediately. Eventually it will drop. So we need to have a bucket underneath to catch it so that we avoid a big mess. And this now represents how important and how strong is actually the air pressure. A big factor why the water does not spill and is stopped there by a piece of paper is it's greatly due to the air pressure. We see the air pressure which we take for granted and we don't feel. It's actually quite strong. It can keep the water in the glass. Let us explain that on the board as well, a little bit more. Now, in the little practical, what we've done was that we filled a glass full of water, and then we placed a piece of stiff paper and we turned it upside down. And we saw that the piece of paper kept in place and the water did not spill, which might sound a bit strange because a glass full of water is quite heavy. The reason for this, obviously, is that there is something that pushes the paper up and does not allow the water to fall, isn't it? which means there is some kind of equilibrium between the weight of the water. How can we represent the weight of the water with an arrow to represent the weight of the water inside the glass? This would be the weight of the water inside the glass. We can represent with this force Fg, meaning the force of gravity, because the weight of an object is actually the force of gravity. And also the force on the piece of paper, which is due to the air pressure pushing upwards on the water there. So how could we draw this kind of forces on the piece of paper due to the air pressure outside the glass? Obviously, there is some equilibrium, some sort of equilibrium between the forces from the air that push the paper up and the force due to gravity, the force due to the weight of the water. So what we had a glass full of water, and we placed on top a piece of paper, and holding it, we turned it upside down, and the paper stayed there. It did not fall off, and kept the water in place. And the water inside the glass has a considerable weight, which we might find strange. Is it possible? How is it possible for air to hold up all this water? Now you may ask, okay, then if we remove this piece of paper, why does the water spill then? Why doesn't it stay in the glass? Which is a very reasonable question. And the answer could be along the lines that the paper being rigid, like kind of solid, offers a surface for the forces from the air to act in this direction to oppose the weight. Because if this piece of paper was not there, the water being a liquid, a fluid, does not have a specific shape, and the air would push upwards inside the water, forming something like a big bubble somehow and displacing the water, so the water will spill out, will spill downwards due to its weight. But the surface of the paper kind of gives a sturdy surface for the air pressure to act, and what causes the pressure of the air pressure? It's the collisions of air molecules with the surface, pushing it up overall, exerting an overall upward force that pushes the paper up, and at the same time the weight of the water inside the glass pushes the paper down. But obviously those two are some kind of equilibrium, and the paper stays there. This is evidence of how important the air pressure is and how strong it is, which we don't feel in our everyday lives. Why don't we feel the air pressure squeezing our bodies? Because the air pressure does compresses us, but our body at the same time has its own pressure that balances this exterior pressure from the air, and we are at equilibrium with our surroundings. The pressure of our body and the pressure of the air outside are at equilibrium, and therefore we don't feel any compression from the air. So this is a demonstration that shows that the air exerts considerable pressure in all the objects in our surroundings.
From Cape to Cairo, Accra to Antananarivo, there are millions of people just like you trying to make a living to make money. And there's no magic way to get rich quick, unless you're Aliko Dangote. You're not Aliko Dangote, are you? No? Well, perhaps we can help you get a little further along the way. With BBC reporters all over Africa, we find the stories, the successes, and the startups that will help you make the most of your money. This is Smart Money.
When you're saying things that degrade women,